Welcome to topic 4103, Ecological Evaluation of Urban Areas. This session is designed to move beyond abstract sustainability language and focus on a practical question: how do we evaluate ecological quality in cities in a way that actually improves planning decisions? Urban areas are not only built environments. They are socio-ecological systems shaped by land use, water flows, vegetation, infrastructure, governance, and everyday human behavior. Because of that complexity, ecological evaluation must do more than describe environmental problems. It must help planners diagnose where ecological quality is declining, understand why those patterns exist, and decide what forms of intervention are most appropriate. Throughout this presentation, we will examine indicator systems, integrated assessment models, spatial analysis tools, ecosystem services, green infrastructure, and biocultural diversity. We will also connect these concepts to planning responses through case-based evidence, especially from Jiangsu Province and Changsha in China. The overall goal is to show how ecological evaluation becomes decision support, not just measurement for its own sake. The lecture is organized in a deliberate sequence. We begin by asking why ecological evaluation is needed in urban areas at all. Then we move into evaluation approaches, with an emphasis on indicator-based systems and the logic behind integrated assessment. After that, we examine the spatial dimension of ecological evaluation through GIS and remote sensing, because ecological quality is never evenly distributed across a city. The next part introduces composite indices such as the Remote Sensing Ecological Index, or RSEI, and then broadens the discussion through ecosystem services and biocultural diversity. Those sections are important because planning needs to connect ecological conditions to human well-being, place meaning, and management capacity. We then shift to prioritization and planning response, including obstacle factor analysis and planning-ready outputs such as green infrastructure networks, zoning overlays, restoration priorities, and monitoring plans. Finally, we anchor the lecture in case study illustrations from Jiangsu Province and conclude with the broader planning frameworks and implementation issues that make ecological evaluation credible in practice. This topic aligns with 5 learning outcomes. First, you should be able to define the basic concepts and principles of sustainable development and environmental planning. Second, you should be able to describe how ecological principles and ecosystem functions relate to spatial organization and urban environments. Third, you should be able to explain how climate adaptation and infrastructure planning support environmental sustainability. Fourth, you should be able to identify the major sustainability frameworks that guide planning practice. Fifth, you should show awareness of ethical responsibility and teamwork in promoting environmentally conscious planning. These outcomes matter because ecological evaluation is never only technical. It sits at the intersection of science, planning, governance, and professional responsibility. As you listen, keep asking how each method helps answer a planning question, what type of evidence it produces, and what limits or ethical issues must be acknowledged before those results are translated into policy or design. Why do cities need ecological evaluation? The simplest answer is that planners cannot prioritize what they cannot diagnose. Urban ecological quality changes unevenly. Some districts may experience vegetation loss, surface sealing, heat stress, habitat fragmentation, or water quality decline much faster than others. Without evaluation, those patterns remain anecdotal. A good ecological assessment helps answer practical questions: where is ecological quality deteriorating? Which drivers matter most? Which interventions offer the strongest benefit? And how should change be monitored over time? It also supports accountability by allowing cities to set targets and measure progress, and it enables comparability across districts, municipalities, or time periods. Importantly, ecological evaluation should not be confused with sustainability branding. It becomes meaningful when it supports prioritization, reporting, adaptive learning, and evidence-based decision-making. In that sense, ecological evaluation sits inside a wider sustainability and resilience agenda, but it contributes something distinctive: a structured way to link environmental condition, urban processes, and planning response. A useful conceptual foundation is to see the city as a socio-ecological system. Cities take in land, water, energy, materials, and people. These inputs are transformed through urban form, mobility systems, green and blue networks, institutions, and behavior. The outcomes are not only economic productivity or service provision. They also include ecological quality, public health, well-being, risk exposure, and resilience. This systems view is important because urban ecological problems are rarely caused by a single factor. Heat stress may be linked to land cover change, building density, mobility infrastructure, vegetation loss, and social vulnerability at the same time. Likewise, ecological improvement is often co-produced through planning, maintenance, regulation, and community stewardship. Ecological evaluation therefore focuses on relationships, not isolated variables. It asks how built form and environmental function interact, how ecosystem processes are altered by urbanization, and how planning can reconfigure those interactions. This way of thinking supports integrated environmental planning rather than fragmented environmental reporting. There is no single method for ecological evaluation, so the choice of approach should depend on the planning question. Indicator-based assessment remains the most common toolkit because it can combine multiple dimensions, build composite indices, and compare places or time periods. Causal frameworks such as PSR or DPSIR are especially useful because they organize indicators in a way that supports interpretation. Other methods serve different purposes. Life cycle analysis and input-output analysis are strong when the goal is to examine resource flows and indirect impacts. Ecological and carbon footprints can reveal demand placed on ecosystems, while cost-benefit analysis or emergence analysis can be used when trade-offs must be assessed in decision terms. The lesson is not that one method is universally superior. Rather, a defensible urban ecological evaluation often combines methods. Indicators may diagnose conditions, spatial analysis may reveal hotspots, and complementary assessment tools may evaluate impacts, trade-offs, or intervention benefits. Good practice means matching methods to decisions, not forcing every problem into a single metric. One of the most useful organizing frameworks is pressure state response, or PSR. Pressure indicators describe the drivers created by human activity, such as land conversion, emissions, infrastructure expansion, or resource consumption. State indicators describe current ecological condition, such as habitat quality, heat load, air or water quality, vegetation cover, or ecological vulnerability. Response indicators describe the actions taken by institutions or planning systems, including green infrastructure, restoration, zoning controls, investment, and policy measures. PSR matters because it turns a list of indicators into a causal narrative. If pressure is rising, state is deteriorating, and response is weak, planners know the system is moving in the wrong direction. If response improves but state remains poor, planners may need stronger measures or more time. In practice, PSR helps structure both evaluation and communication. It also prevents an overly descriptive approach by asking not just what ecological quality looks like, but what is driving it and how governance is responding. A robust indicator system does not happen automatically. It depends on explicit methodological choices. First, scale must be defined. Are we evaluating neighborhoods, districts, cities, or city regions? The answer affects data availability and the kinds of patterns that can be detected. Second, domains must be chosen carefully. Ecological evaluation may involve environmental, resource, economic, and social variables, but the mix should reflect the question being asked. Third, data quality matters. Administrative statistics, monitoring data, and remote sensing each provide different strengths and weaknesses. Fourth, normalization is essential because indicators come in different units and directions. Some higher values are desirable, while others indicate deterioration. Fifth, weighting determines how much influence each indicator has on the final result. Methods such as AHP rely on expert judgment, entropy uses data variation, hybrid and variable weight approaches combine logic and responsiveness. Finally, defensible systems require sensitivity checks and transparent documentation. Without that transparency, composite scores can appear precise while hiding important assumptions. Urban ecological conditions are spatially heterogeneous, which is why GIS and remote sensing are central to this field. A city can contain cool vegetated corridors, heat-stressed industrial zones, flood-prone impervious districts, and relatively stable peri-urban ecological areas all at once. Spatial analysis makes those contrasts visible. Remote sensing provides repeatable measurements of land cover, vegetation, moisture, temperature, and built-up intensity, while GIS allows those layers to be combined with socio-demographic, infrastructural, and hydrological information. This matters for planning because interventions are spatial. A planner needs to know where restoration is most urgent, where green corridors can improve connectivity, where land use controls should be tightened, and where ecological benefits can be maximized for vulnerable populations. Spatial tools also improve monitoring by allowing comparisons across time. Instead of relying on narrative claims that ecological quality is improving or worsening, planners can observe map change and identify hotspots, transitions, and clusters that demand differentiated action. Composite indices offer a way to summarize ecological environment quality without ignoring multidimensionality. A good example is the Remote Sensing Ecological Index, or RSEI. RSEI brings together greenness, wetness, dryness or built-up intensity, and heat into a single score that can be compared over time and across space. Conceptually, this is powerful because it condenses several environmental signals into one interpretable indicator while retaining a clear ecological basis. In the Changsha case, RSEI was used to examine spatio-temporal change between 2003 and 2018. The study found that average ecological environment quality declined from 0.532 in 2003 to 0.500 in 2014, then rose to 0.523 in 2018. That means there was partial recovery, but the overall tendency still reflected urbanization pressure. The key value of RSEI is not just that it produces a number. It produces a map-based diagnosis that helps planners identify degraded areas, detect change, and link environmental quality to land use dynamics and planning interventions. Ecological evaluation becomes more planning relevant when it is linked to ecosystem services. This shifts the discussion from environmental condition alone to the benefits ecosystems generate for people and urban systems. Regulating services such as cooling, runoff control, and air quality improvement are especially important in cities. Cultural services also matter, because urban green spaces provide recreation, place attachment, and everyday contact with nature. Provisioning services may be less dominant in dense cities, but they still matter in broader urban regions. The advantage of an ecosystem services lens is that it makes trade-offs visible. A patch of vegetation is not only green cover on a map, it may also reduce heat, improve stormwater management, and support well-being. The Urban Ecosystem Services Index provides one way to assess the intensity of services provided by urban ecosystems. For planning, this means ecological evaluation can support targeted green and blue infrastructure design, rather than treating all open space as functionally equivalent. Traditional ecological assessments often focus on physical assets alone: parks, trees, wetlands, corridors, or other green and blue elements. Biocultural diversity thinking broadens that picture. It asks not only what ecological assets exist, but how they are used, experienced, governed, and cared for. This adds lived, cultural, and stewardship dimensions to ecological evaluation. In practical terms, a green area with high ecological value but poor accessibility or weak stewardship may perform very differently from a smaller area that is well connected, socially meaningful, and actively managed. For green infrastructure planning, this matters enormously. Decision support tools based on biocultural diversity can help planners identify where physical investment should be paired with participatory management, accessibility improvements, or local stewardship mechanisms. In other words, ecological quality is not only material, it is also relational. Adding these dimensions makes ecological evaluation more realistic and more useful for implementation, because it reflects how urban green systems actually function in people's lives. A common criticism of composite ecological assessments is that they produce rankings without telling decision makers what to do next. Obstacle factor analysis addresses that weakness. The idea is straightforward. Once an index has been calculated, the next step is to identify which variables are most strongly holding back improvement. In the Jiangsu case using PSR, variable weights, TOPSIS, and obstacle degree analysis, the method did more than rank cities. It diagnosed the constraints behind performance differences. That is important because two places can receive similar overall scores for very different reasons. One city may be constrained by weak response capacity, another by resource pressure, and another by environmental degradation associated with industrial structure. By identifying obstacle factors, planners can move from general concern to targeted action. This is a major step in making ecological evaluation actionable. It turns a static assessment into a prioritization tool that can support differentiated strategies across territories rather than one-size-fits-all policies. The real test of ecological evaluation is whether it feeds a planning loop. Measurement should inform decision-making, decisions should guide implementation, and monitoring should update future priorities. In practical terms, the outputs of ecological evaluation can support green infrastructure network plans, zoning overlays, restoration priorities, ecological red lines, climate adaptation measures, and targeted monitoring plans. The Changsha study is especially useful here because it linked ecological environment quality trends to territorial spatial planning response. It showed that scientific planning and stricter control can help slow or reverse degradation, especially where industrial land expansion has concentrated ecological pressure. The broader lesson is that ecological evaluation is not finished when the maps are made. It is finished when planners can translate those maps into concrete actions, measurable targets, and phased interventions. That is why planning response must be built into the evaluation design from the beginning, not added as an afterthought. Ecological evaluation in urban areas also needs to be legible within broader planning and governance frameworks. At the international level, the Sustainable Development Goals, especially 11 Sudanese pounds, provide an important reference point for sustainable cities. The Paris Agreement adds climate mitigation and adaptation context, reminding planners that ecological quality, urban resilience, and climate governance are deeply connected. The new urban agenda frames sustainable urbanization more broadly, emphasizing inclusion, resilience, environmental quality, and long-term planning. In European policy contexts, the European Green Deal offers another reference point for linking environmental quality with transition agendas. These frameworks do not tell planners exactly which indicator to use, but they do shape what gets measured, how targets are justified, and how urban ecological evaluation is communicated to policymakers. In teaching and practice, this matters because students and professionals need to recognize that local ecological assessment is part of a wider governance architecture, not an isolated technical exercise. Even the most sophisticated ecological assessment can be weak if implementation is careless. Technical robustness requires good data quality, transparent methods, comparable spatial units, and sensitivity checks. But credibility depends on more than that. Ethical responsibility matters because ecological evaluation can shape investment, regulation, and public narratives about which areas are valuable or neglected. If methods are opaque, biased, or insensitive to vulnerable populations, the resulting decisions may reinforce inequality rather than improve sustainability. This is why stakeholder awareness, environmental justice, and responsible communication of uncertainty are essential. Teamwork also matters. Ecological evaluation typically requires collaboration among planners, GIS analysts, ecologists, statisticians, and local stakeholders. A reproducible workflow, clear role distribution, and transparent documentation make results more trustworthy and easier to update over time. So LO5 is not peripheral to this topic. It is central. Good ecological evaluation is both scientifically sound and professionally responsible. Another key lesson is that the end product of ecological evaluation is not just an index value. Decision makers need planning-ready communication. That usually means maps showing hotspots, vulnerable zones, ecological corridors, or priority restoration areas. It may also mean benchmarks, target values, and trend lines that indicate whether ecological quality is improving. Narrative explanation is equally important. Planners need to understand not just where problems are located, but how pressures, state conditions, and responses relate to one another. Finally, evaluation should lead to decision products such as priority lists, phased interventions, and monitoring frameworks. A useful rule of thumb is this: if a planner cannot point to a map, a decision list, and a monitoring plan, the evaluation is incomplete. Communication is not decoration added at the end. It is part of the assessment's usefulness. Clear communication turns evidence into something that governance systems can actually act upon. The case studies bring the whole topic together. In Jiangsu Province, one study developed an eco-city evaluation method using spatial analysis, ecological vulnerability, and an index framework structured through PSR logic and weighted with AHP. That approach emphasized spatial pattern and differentiated strategy. Another Jiangsu study evaluated urban ecological civilization across 13 cities using an extended PSR framework combined with exponential variable weight, TOPSIS, and obstacle degree analysis. Its value lay in ranking and diagnosis. Overall performance improved over time, but regional differences remained strong, and response capacity was relatively weak. In Changsha, the RSEI-based study focused on ecological environment quality over time and linked results to territorial spatial planning. It found decline followed by partial recovery, with urbanization and concentrated industrial land as important drivers of degradation. Together, these cases show that different methods produce different decision outputs. Some reveal spatial patterns, some highlight trajectories, and some diagnose the constraints blocking progress. Good planning practice may need all three types of insight. To conclude, ecological evaluation of urban areas should be understood as decision support, not as scoring for its own sake. It helps planners diagnose condition, compare places, identify drivers, and prioritize action. The method must fit the question: indicator systems, PSR frameworks, remote sensing, GIS, ecosystem services assessment, biocultural diversity tools, and obstacle factor diagnosis all serve different but complementary purposes. The most important shift is from measurement to response. Ecological evaluation is only useful when it informs planning outputs such as green infrastructure strategies, spatial controls, restoration priorities, climate adaptation measures, and monitoring systems. It also connects strongly to related topics in environmental planning, climate adaptation, and nature-based solutions, because those fields all depend on high-quality diagnosis. Finally, credible practice requires methodological transparency, ethical responsibility, and collaborative implementation. When those elements come together, ecological evaluation becomes a powerful bridge between urban ecology and planning action.